Okay, so today is day 9. We're going to be looking at velocity. Let's first do a little bit of warm-up. Make sure that we review some of these important things. First of all, converting 35 centimeters to meters. One of the shortcuts to doing this is to just slide the decimal point over 2 places. So we start off with the decimal point right there next to the 5, and we go over 2 to the left, 1, 2. We end up with 0.35 meters. If you want to throw the 0 up front, you can. But to go from centimeters to meters, you always have the decimal point move over twice. Okay, now in today's lesson, we're going to be looking at some new equations. And to solve these, we need to remind ourselves about how to do this algebra. The first couple are very, very simple. The second couple are a little bit tricky, and a lot of people get them wrong, even though they look easy. They assume that it's easy, but it isn't. And so we got to learn a little trick. Okay, first of all, find x. Go ahead and pause the video. Try to do this on your own, and then start the video up again to see if you got it right. Okay, so we want to get the x by itself. Right now it's being divided by 6, and so I do the opposite. I multiply both sides by 6, and I get 180 equals x. The 6 on the bottom and the 6 on top cancel. Similar kind of a thing for number 3. Pause the video and try it on your own. We're going to multiply both sides by 3, so we get 60 is equal to x. Okay, those are the easy ones. Number 4. Scientist A is debating an issue with scientist B. Scientist A says, "This report must be wrong. The trend line is forced to be linear when it should be a curve. This is so obvious that any third-rate scientist should be able to see it clearly." Is this a valid criticism, or is it an ad hominem attack? Okay, now in this statement here, they're talking about the mathematical process. The trend line is forced to be linear. They say it should be something else. It should be a curve. So they are talking about the data. So this is a valid criticism. Now you might want to think that, hey, they're talking about third-rate scientists, and so therefore it is attacking the scientist. Well, it's sort of, but they're not saying don't believe this scientist B because he's a third-rate scientist. That's not the argument at all. They're saying that scientist B made a mistake, and everybody, even the poor scientists, no matter where they are or who they are, even the poor scientists would be able to understand the right way of doing things. So that's okay. Once again, if they had said, don't believe scientist B, he's third rate, just ignore him, that would be an ad hominem attack. I hope that you understand the difference between the two. Okay, now then, let's look at problem number 4. This is one that looks apparently like it's easy, but it's actually kind of tricky. We want to get the t by itself. The t is in the denominator, in the bottom of the fraction. So we can't just simply divide both sides by 240, because the t would still be at the bottom. It'd be 1 over t. And we don't want that. We want plain old t. So one thing that we can do to help us out is to think of this as a proportion. 80 over 1 equals 240 over t. And we could, if we wanted to, cross multiply and divide. People are very familiar with that and are very comfortable with that. But there's an even easier way. There is a property of proportions that say that we can switch diagonals. And so instead of 80 over 1 equals 240 over t, we'd have t over 1 equals 240 over 80. And we don't even have to think about this over one part. We could scribble that out, or we could whiten it out. And so we just simply switch the variable at the bottom with the number up front. That's called switching the diagonals. And so we get the answer here of 3. In this case right here, again, we can switch diagonals. And so I can just write down immediately t is equal to 28 divided by 7. And so t is going to be 4. That is a technique that we're going to be using many times throughout the year. So it'd be really good for you to get familiar with that. It's a variety of doing the cross multiplying and dividing. Once again, it's called switching diagonals. Okay, we're going to be talking about lots of story problems with objects moving in different ways, and we need to recognize different phrases that mean that an object's speed is 0 miles per hour. So you could say that it is stationary. By seeing those words, we can assume that the initial speed is 0 miles per hour. We could say it is standing still. We could say it is motionless. All of those are phrases that mean the speed is 0. Okay, going through the step-by-step process to solving story problems, we first draw a picture and we label it with the data and variables along with the frame of reference. We need to state the desired variable, make it equal to a question mark. Then we convert units if need be. Next, number 5, we find the raw equation that has the desired variable and everything else in the equation we know. Then we substitute in the known values. So we should have only one variable left over after the substitutions. Everything else is numbers. And finally, report your answer with the proper units. Go ahead and read the main ideas from yesterday. Today, you'll be getting a grade on homework 9. You should be able to do that. And hopefully we'll have time to do a lab as well. And there are responses in Schoology for that. Next quiz is a long time from now. Today's day 9. Purpose, I will understand the physics definition of velocity and be able to calculate it. Relevance, this is how some police officers catch speeders. Success, we will find the velocity of a ball rolling on a counter. So here's the equation that defines the average velocity of an object. This is the same delta x that we saw last lesson. It's the displacement. It can be either positive or negative. It's going to have units of some kind of a length, meters, kilometers, miles, something like that. Down here, t, we talked about this yesterday. The t is going to be time, and it's measured in things like seconds. Seconds is the most common. That's abbreviated s, or it could be SEC if you're a little bit more old-fashioned, but generally you'll see it as a single s. Time is always positive. Okay, so the average velocity has this symbol, v with a subscript AVG. We read that as average velocity. So t, the time, is always positive, but the displacement can be sometimes positive, sometimes negative. It is positive if it's moving to the right, or it's positive when it's moving up. But whatever that is, positive or negative, it's being divided by a positive. So that means that whatever sign the displacement is, the average velocity will have the same sign. So if it's moving to the left, we're going to get a negative average velocity. If it's moving down, it's a negative average velocity. If displacement is negative, then it is moving down or left. So the sign tells us the direction, and the digits tell us how fast it's going. So that means that V is a vector. It has two parts. The magnitude is the speed, how fast it's going, and the sign tells us the direction, just like with displacement. Okay, so let's use this equation to solve some problems. Number 1. A teacher drives 4,800 meters in 180 seconds to reach the coffee shop. What was the teacher's average velocity? Okay, so we don't have a symbol up front, we don't have a sign, so that means that we're going to assume that it's a positive. Positive means that it is going to the right. So here's the car in the original location, and it drives to the right to another location. The distance, the displacement, is 4,800 meters. And the time for this to happen is 180 seconds. So this motion arrow symbolizes a movement of 4,800 meters over a period of 180 seconds. That is what we know. What we want to know is, what was the teacher's average velocity? That's V with a subscript AVG, and we have a question mark. We don't know what that is. That is our picture, and that is matching the data and the variables together. And that's the third step, writing down the desired variable. Notice that I have not included a coordinate system, so I better do that before I forget. Now in this case, we don't have anything measured in relation to that exact spot. We don't know exactly where the origin is, so we can put it anywhere we want. So I'm going to put it down at the original location. That's my traditional way of doing it, if we're not given some specifics. Okay, next, step number 4. Are the units compatible? We have plane meters here. We don't have any other length units. We don't have inches or centimeters or kilometers, so nothing is conflicting with that. Here we have the unit of time being seconds. I don't have any other units of time anywhere being hours or minutes or weeks or anything like that, so there's nothing to conflict with that. So we're good there. Do we need to make anything negative? We've already talked about that positive, and time is always positive, so we don't need to worry about any negatives. So that's steps 1 through 5. Step number 6, find the raw equation that has the desired variable. So we are looking for the average velocity, and this equation has it. We know the other parts. We know the displacement on top, and we know the time on the bottom, so we can use that equation. Now we do our substitutions and our algebra. We're looking for the average velocity, so that stays letters. The displacement is going to be 4,800, and that's meters, and the time is 180 seconds. So if I do that division in my calculator, it's going to be 26.666. I'm going to round it to be 26.7. That's the digits part. But I also have these units here. Now remember, we treat the units just like x's and y's and other variables in algebra. The meter is like an x and the s is like a y. If I had x over y, I couldn't cancel them out. I could not combine them at all. They would just stay separate. So the meter and the seconds, they don't cancel or combine. We just keep them written down as a fraction. And so I'd read this as the average velocity is 26.7 meters per second. Whenever I see a fraction with the units, I say at the top, and then per for the fraction bar, and then seconds on the bottom. As every second passes by, the car moves 26.7 meters. That's what that would all mean. Okay, now we have other units that could be possibly for average velocity. You're familiar with miles per hour. Technically, that would be miles on top, hours on the bottom. If I was traveling 55 miles per hour down the freeway, that means that in 1 hour, I'd be able to travel 55 miles. In other words, 55 miles per hour that I travel. So any kind of unit of distance is on the top, any kind of unit of time is on the bottom. I could have kilometers per minute. Or if something was really, really slow, like a glacier, I might measure that in inches per year. A plain old unit of distance on top and a plain old unit of time on the bottom. Okay, so let's practice looking at these different kinds of story problems and discerning what kind of information we're given. Number 3, label the appropriate measures as either V average, X sub F, X sub I, displacement, or time. We need to also think, are all the units compatible, or do we need to change anything to be negative? So the first problem here, a 500 kilogram car moves for 30 seconds to move from a point 40 feet on the left side of the hydrant to a spot 80 meters on the right side of the hydrant. During this time, it moved 4 meters per second. The total distance traveled was 120 meters. Okay, so we have got lots of information here. We need to be able to discern what number goes with what variable. So let's first of all look for the average velocity. We want to look for some kind of a unit that's a fraction with a plain distance on top and a plain time on the bottom. Fraction, looking for a fraction, looking for a fraction, looking for a fraction, looking. There's a fraction. Meters per second. So I'm going to circle that, and I'm going to call that average velocity. Okay, the next one is an X. So I'm looking for something with a plain old distance, like a meters or a feet or an inch, something like that. So let's see here, that's a mass. Here we have time. Here we have 40 feet. Here we have 80 meters. And here we have 120 meters. All of these could be X's. We have 3 different kinds of X's. We got to figure out which one is which. Anyway, I'm going to circle all of these though, and I'm going to put down just an X, and then we'll figure out what kind of an X it is in a moment. Since they have plain old length units, we know that they are X variables. Now we've got to look at the context of the question or the statements to see which one is the final, initial, or displacement. It says here that it moves from a point to another spot. So from, that must be the beginning, the initial location. And it's going to a spot. So that must be the final location. And then down here, the total distance traveled. So that is the displacement, delta x. Are the units compatible? In this case, no, they're not. Here we have the distance unit of feet, but in the velocity, we incorporate the distance unit of meters. So that's a conflict there. We got to change it. And here we have meters, there we have meters. So this feet is bad. We need to convert that. I'm going to put a CONV next to that. How about our time unit? Here we have seconds. Do we have any other units of time? Oh, here is 30 seconds. That was our t variable, and those units match up, so that's okay. I don't have any units of time anywhere in this situation that are like hours or minutes or days, and so there's no conflict in the time units. Anything need to be negative? Let's see here. Time is always positive. Here, this is 40 feet on the left side. Left side of the origin is traditionally going to be negative, so I'm going to put a little negative sign there. Here, we're moving to a spot 60 meters on the right side. That's positive. Right side of the origin is traditionally positive. It moved at a rate of 4 meters per second. Okay, it's going to the right, from the left side to the right side, so this is positive. And the total distance traveled then, the displacement, if it's going to the right, will also be positive. Okay, with that kind of stuff in mind, go ahead and try number 4 on your own. Would you please pause the video, give it a try, and then we'll see if you got the same thing as me. Okay, before we go on to this problem, let's just note here that we never did anything with this 500 kilograms. That is the mass of the car, and we don't have any equations that deal with mass, so that's extraneous information. Please note that throughout the year I give you extra information that you will not be using in story problems. This is a good skill for you to be able to discern, because when you're solving any kind of problem in life, there's going to be lots and lots of numbers that you could measure, and you have to figure out which ones are pertinent to the situations and which ones are irrelevant. Okay, so problem number 4, we need to figure out which variables these things are. Here we have a basketball falling 8 feet. The ball starts off 2 feet above the rim. It takes 0.4 seconds to travel at an average rate of 20 centimeters through the net and towards the ground. It ends up being caught 6 feet from the, it says spout. It should be, I don't know where that spout came from, 6 feet from the ground. Okay, so things are, let's see here, we're measuring this from above the rim, and let's see here, down here they're measuring it from the ground. This is not good. Let's change my mind here for a second. It's caught 6 feet from the rim. There we go, that's much better. So both of these distances, 2 feet and 6 feet, are measured from the rim, so I'm going to make the rim my origin. So anything above the rim is going to be positive, anything below the rim is going to be negative. Okay, let's talk about this here. A basketball falls 6 feet. We have a plain old unit of feet. That's a length distance. So that's going to be an x. And that is how far it falls, how far it travels, the distance it travels. So that's delta x. It starts off 2 feet above the rim. Again, a plain old unit of length, and so that's going to be an x of some sort, and it says it starts there, so that's going to be an x sub I. Next, it takes 0.4 seconds. You should recognize that as a time unit, so that's t. It travels at an average rate of 20 centimeters per second through the net. So that's a rate of traveling, that's going to be a velocity. And we just have average velocity right now. Later on, we're going to have other kinds of velocity, and we'll go into that detail later. Okay, it ends up being caught 6 feet. That's a plain old unit of length, so that should tell us it's an x. And it ends up being caught there. The ending, the final location is going to be 6. Okay, so that is labeling all these parts, labeling all the variables. Are the units compatible? No, they're not. Here we have feet, there we have feet, there we have feet, but over here we have a unit of length of centimeters. So this length unit is not compatible with that length unit, and things aren't going to cancel out appropriately. So you better convert this one. Time, we have seconds there and we have seconds down there, so those are compatible. So everything else is okay. Any negatives? It's falling 8 feet. It's falling downwards, so that means that this displacement had better be negative. It starts off 2 feet above the net. Above the net means above the origin, and so that's going to be positive. Time is always positive. Then we have the average rate of falling. That's going to be the velocity. It's falling downwards, and so that's going to be negative as well. The next number I see is the 6. It ends up being caught 6 feet from the rim. Now this is on the lower side of the rim because it has fallen. Let's see here, it falls through the net, so that means it's going through the rim and ending up below the rim, so that means that this is going to be negative. Next. A car's velocity is positive 40 meters per second. It moves for 5 minutes. Find the displacement. Okay, so the velocity going positive, so that means it's moving to the right. We don't really know where it's starting or ending. We just know that it's moving to the right. So there's my picture. My origin. There's no obvious place according to the story problem, so I'm just going to put it at the original location. Positive to the right, as tradition says. So there's my picture and the coordinate system. Step number 2, match the data and the variables. This first number is the velocity, the average velocity. The second number is going to be the time. That's step number 2. Matching data and the variables. Number 3, state the desired variable. It says to find the displacement. So that means that I'm looking for the delta x. I can circle find if I wanted to. That's step number 3. Step number 4, are the units compatible? Here I have meters, that's a length unit. I don't have any other length units. I don't have inches or centimeters, so I don't need to worry about that anymore. But I have a seconds here in the bottom, but here I have minutes. Those are not compatible. So that means I needed to convert, and it'd be easiest to convert the 5 minutes to be 300 seconds. And then I scribble out the 5 minutes. That is step number 4. Step number 5, do I need to make anything negative? Well, this is given to me as positive, so I know for sure that's going to be right. And time is always positive, so that's all right. We don't need to do anything more for step 5. Step 6, find the raw equation that has the unknown. Okay, now I have 2 equations that have the delta x. I have yesterday's delta x equals x of f minus x of I. And I have today's average velocity is equal to delta x divided by t. Both of them have delta x in it. So which one do I use? Well, you have to have numbers for everything else in the equation. I do not know the final location. I do not know the initial location, so I cannot use this first equation at all. This one I can use. Let's substitute in our numbers. The average velocity is 40 meters per second. The delta x is what I'm looking for, so it stays letters. And then the t is 300 seconds. To solve for delta x, I multiply both sides by 300 seconds. So over here, the 300s cancel, but the seconds also cancel, just like x's and y's and m's and p's in algebra. So on the right-hand side, all I have is the displacement. On the left-hand side, I multiply the numbers, and I get 12,000. When I look at the letters, this s is sort of like over 1. So that's an s on top, there's an s on the bottom. They cancel, leaving just plain old m for meters. So the displacement, which is a distance, is measured to be 12,000 meters, and that makes sense. If I came up that the displacement is equal to 12,000 seconds, that doesn't make any sense at all. You can't have a distance measured in seconds, and so that would indicate that we got something wrong. We're done with this problem now. Try number 6 on your own. Pause the video and then turn it back on to see if you get the same thing as me. Number 6, car's velocity is positive 45. So I'm going to draw the car going in the positive direction. It moves 15 meters to the right. Find the time needed to do this. The origin can go anywhere we want. It's convenient to put it there. That's step number 1. Step number 2, match the data. This is the average velocity. This is the displacement. We're trying to find t. That is what we know, and that's what we want to know. Now, are the units compatible? We have meters here, we have meters there. That's good. Then we have seconds here, and no other units of time anywhere, so we're good with that. Step number 5, anything negative that's given to us as positive, so we know that's for sure right. And the displacement. It's going to the right, so that means that displacement is going to be positive. We did not have a positive sign there, so I couldn't assume that it was positive. I had to look at the context. If I have a positive sign or a negative sign next to some kind of a measure, you know for sure that that's going to be the case when we do our substitutions. Okay, so we got step number 5 all done. Step number 6, find the raw equation. We're going to use our new one from today. Write that down, and then we're going to substitute things in. We have 45 meters per second is equal to 15 meters divided by the unknown. Okay, we have a plain old number equals a fraction with the denominator having the variable. So what we're going to do is switch the diagonals. We have 15 divided by 45. Those digits result in 0.33. 0.33333333. But with our units here, we have meters divided by a fraction. Meters divided by a fraction is the same thing as meters times the reciprocal, S over M. Remember that dividing by a fraction is the same thing as multiplying by the reciprocal. So when we multiply by the reciprocal, the m's cancel out, leaving just plain s's. And that makes sense to have time measured in seconds. Refocus on today's purpose. I will understand the physics definition of velocity and be able to calculate it. Okay, so the physics definition of velocity is V average is equal to the displacement divided by time. And it's a vector, which means that it has both the speed, the digits, 0.3 digits like 45 meters per second, but it also has direction, speed and direction, the direction shown by the positive or negative, whichever. So your speedometer on your car only tells you speed, it doesn't tell you which way you're going. So speed and velocity are slightly different. Velocity gives you more information. It's the speed plus direction. Speed is only how fast you are. Okay, number 7, write the equation as to proportion. V average over 1 is equal to the displacement divided by time. Note that the V and the X are both on top of the fraction. This is a direct relationship. What happens to the value of V as you put in bigger and bigger values for X? As the top of this fraction gets bigger and bigger, the value of V is going to also get bigger. Six over 1. And then I put in a bigger number, 8 over 1, 10 over 1. As the top gets bigger and bigger, the velocity is going to get bigger and bigger. Number 8, write the equation as a proportion. V average all over 1 is equal to delta x all over t. Note that the V and the T are on opposite sides. This is on top, that's on bottom. Let's see here. This is an inverse relationship. What happens to the value of V as you put in bigger and bigger values for T? Well, let's look at fractions that all have, let's say, 1 on top. But the bottom gets bigger and bigger. Start off with 1, then 2, then 3, then 4. The decimal version of this is 1. The decimal version of that's 0.5, 0.33, 0.25. So you can see that as the fractions get bigger and bigger on the bottom, the value of it gets smaller and smaller. So what happens to the value of V as we get bigger and bigger T's? It gets smaller. V average gets smaller. Number 9. Whoop, I didn't move my paper up. Sorry about that. So there you can pause the video and copy that down if you so choose. Number 9. Derive a new equation by combining our two equations into one. Our first equation that we learned yesterday was the displacement is equal to the final location minus the initial location. And then today's V average is equal to the displacement divided by time. What I'm going to do is to take this, which is equal to displacement, and substitute it in for the delta x in that equation. And I come up then with a brand new version of things. Average velocity is equal to final location minus the initial location divided by time. And that's going to be a useful equation for different situations, such as this one. Number 10. A train starts off 200 meters from the right side of a sign. After 40 seconds, it's 1 kilometer on the right side of the sign. Find the average velocity. Okay, so here's the sign, and everything is measured relative to that sign, so I'm going to make that the origin, positive to the right. It starts off 200 meters on the right side. So here's my train. Nothing fancy in the drawing. And then it's moving away from the sign because it ends up being much farther away. Like that. There's my picture. Now let's get the information. X sub I is 200 meters, and it ends up X sub F 1 kilometer. And this is over a time of 40 seconds. That's what we know. That's step number 2. Step number 3, finding the desired variable, we want to find the average velocity. So we are looking for V average, unknown question mark. Number 4, step 4, are the units compatible? No. We have kilometers here, meters there. So we got to make this into meters, 1,000. Scribble out the kilometers. Do we need to make things negative? No, everything's on the right-hand side, so it's all positive. Time is positive, so that's good. Number 6, find the raw equation. We're going to use this equation right here now. We're looking for the V average, and we know all these others. We cannot use directly this V average is equal to displacement divided by time because we're not given the displacement. Yes, we could figure